Okay, welcome back. This is a little short video, maybe not so short, as short as I would like, but I wanted to go through, and this will be a mix of some fresh content this year and a little bit from last year, the homework number 3, the homework that involves the simulation of cardiac myocyte membranes and how you handle that. Generally, everything's fine. Hopefully you'll understand if you lost some points and be able to ask us about it. The real big point here is that a homework like this, a simulation assignment like this, is really a great opportunity to think about experimental design, to think about how you set up experiments, how you evaluate them, how you present them, skills that I would argue are just really valuable generally. You'll certainly need them again in this course. And so this was our first real chance outside the labs to really go through this. So let's spend a little time talking about things to know, things to take note of, things to improve for next time. As you'll see in the slide here, where we summarize some of the general presentation, writing, kind of layout questions, you all did fine except for one topic, and that is the layout of graphs. And there are standards in any sort of report, I would argue, whether it's for school or certainly for a scientific journal publication, and I would argue even for the kind of reports you may very well be writing in your jobs in the future. And we want to go over some of those. So you'll see some examples of that later on. You can see here, that's really the major point where we saw some weaknesses that we wanted to address. And we'll be covering those, like I say, where they come up naturally in the course of the questions. So we'll jump here to some other content from before and then just march through the questions. But keeping in mind that what we cover here really is meant to be general and hopefully can guide you going forward into all kinds of other experiments that you will inevitably design and analyze and describe to the people around you. And hopefully that'll be helpful. So let's go through a couple of the questions and see where things landed. First question was all about evaluating the model in terms of its ability to reconstruct this all or nothing behavior that we're told to describe the initiation of the action potential. So all or nothing means we get no response until we get a response. Now, that's an oversimplification that's unlikely to arise even in nature, or maybe especially in nature, and so that the simulation doesn't work in quite such a dramatic fashion would be totally logical. In fact, it's totally logical that even when we inject current into a cell that does not lead it to reach a threshold, it should still change the voltage in that cell. So we should see an increase in membrane voltage just because we've injected some current into it, even if it's not enough for a threshold. And so you tested these, most of you came to the same conclusion that the model does reasonably well, actually pretty well, I would say. The differences between an impulse amplitude or duration that would take it from no response to a full response were really small margins. I mean, percentage-wise, we're talking, really pretty minor changes in the parameters that would bring us through that threshold space. So overall, I think the model captures it reasonably well. I think most of you agreed with that in your own conclusions. Before we move on to the second one, though, I want to show examples of some of the plots that we saw and some suggestions about ways to improve them. So here's an example, not from this year, from a previous year. I'll be candid about this. And you can see a few markings on it. In the scientific genre of writing, we don't include titles on figures. The caption contains the title. So the figure is really the graphical information. It can definitely have a legend, as this one does. Obviously it has to have axes very clearly and completely marked. So not just the units, but also what the quantity is that we're actually displaying. So these are minor things, but little things you can just kind of check off to make sure you're doing them correctly, because without them it becomes just challenging to appreciate what the figure contains. And similarly, the caption has to help the reader. The goal of the caption is that a reader should look at it at a glance, see the title, in this case, representative action potentials. That's a bit of a vague title. I oftentimes want to find something a little more specific than that, so that the reader, again, can at a glance say, oh, that's what this figure is about, and then read enough in the caption to understand more of the details. And this was a relatively short caption that could have contained more information. The other thing that's a pleasant reality compared to many years ago is that we can use color. I encourage you freely to use color. Most journals accept color these days. Anything electronic is just as easy to produce in color as it is in black and white, which was different back in the days of print articles. I don't know when you last read an article in print, but it's getting less and less common in science to be reading an article not on your screen. So use color. And you can see the challenge in this case. The student tried very hard here to create different line types and kind of encode them with different amounts of fill and shades of gray, and all became very complicated, but still ultimately pretty hard to see, pretty hard to tell these lines apart and get the real essence of the finding that is supposed to be encapsulated here. So there's just a couple of things about figures to keep in mind. Overlay plots are definitely to be encouraged. So make sure that you're comfortable using them, that you know how to produce them in MATLAB. There are a couple little tricks as usual. You can even control the colors. There's a number of features you can play with. In a case like this with multiple action potentials, the legend is absolutely crucial. That really tells the reader what the difference is among the different plots, and that obviously is essential. This one you can see has a much longer caption. The title is more extensive, action potentials with different degrees of stimulation. That's a really informative title. So try for informative titles, enough detail in the caption to convey to the reader what's going on. Don't go into the results necessarily. Definitely don't start discussing what the results are in the figure. That's more than the caption is really meant to contain. That's what the text is for. But we can certainly, as this plot shows, give a pretty clear idea of what's there to be seen and how to read it. Zooming in is another great feature. So when we have details that the overlay plot doesn't show, then we should zoom in on parts of interest, parts we want to draw the reader's attention to. And here's a nice example of that, where that early rising phase of the action potential is really the point of interest in that problem. So why not zoom in on that? And it really helps pull apart the different cases and the different responses to those different cases. So always think about how you can make the most of the details of the figure. Sometimes you can include a zoomed in portion embedded somehow in the big picture version of the figure. There are lots of interesting visualization approaches to use here. So that was just determining whether there was a threshold and whether that threshold seemed to show an all or nothing type behavior. Now we come to the more quantitative part in some regards, where I asked you to find 20 different values where you just barely could elicit an action potential, and then plot those and then use them to help you uncover something a little bit deeper about the behavior of the membrane. That was really the goal here. So here's a simple example of just a table I made with 5 different values, and I have stimulus amplitude, stimulus duration on both axes, and I just marked a yes or no, whether or not there was what I would call a normal-ish action potential generated. And I could even sort of imagine a line between the two. I could even draw a line between the two that looks something vaguely like this. There's lots of artistic impression here, of course, because I'm interpolating and it's a fairly coarse sampling that I've done here. I can use color to highlight those differences. That can also help in the visualization. But the real question here is to think about what those results tell us about the underlying behavior of the membrane. And this is fairly common in simulation, where you get some results, you stare at them for a while, you think you have some idea what they might mean. Then it's time to go back to the underlying mechanisms, the physics, the chemistry, whatever, and say, does that result really correlate or correspond with my understanding about this phenomenon, this behavior? And this is a great problem in which to do that. And let me explain how. Most of you tried fitting the data, or many of you at least tried fitting the data. Definitely a sensible thing to do, right? When we fit data, we get an analog function that allows us to describe in closed form what the relationship is between these two parameters, especially in the context of the parameters being defining whether a tissue will stimulate or not, or whether a cell will stimulate or not. Here's, for example, a simple linear fit of the intensity and the time, the duration of the actual pulse. And we see that gives us a fit. There's an R squared value. That's sort of a figure of merit. Hopefully you've seen those before. 0.85 is pretty good in lots of situations. And you can see the red line, does sort of track through the individual data points. You, under some circumstances, could convince yourself that a linear relationship is a pretty good representation. But of course, you're going to try other things. So here's what we get. When we try a log function, we see what the logarithm of the values would be. And there we see even a better fit. 0.96 is the R-squared value. And then we say, well, we got to try higher order polynomials than just a straight line. So we allowed a quadratic function as well as the linear component. So a full second order polynomial response. And there we see even a better fit, 0.97. Is 0.97 significantly different from 0.96 in this case? That would be debatable. You'd probably need more data before you could really be confident that that small difference was really meaningful. And finally, of course, you got to try exponents, right? Because exponents come up so often. So here's an exponential fit. And here we see, the R-squared value is a little bit lower, 0.95, still a very respectable R-squared value. So we have all these fits, and they all look okay. And so what would you do about it? Well, one approach, obviously, is to get more data. This is always true in statistics. The bigger the n, the more confidence you have in the result. And that would make perfect sense, definitely to be encouraged. Another approach is to say, well, what is it actually capturing here? What is the underlying physics of what's going on? And I have these 4 fits. So here we see them actually all together, all the 4 different fits, and we can look at the different R-squared values. But again, what are we really capturing here? How do we think about this? So one of the ways we see more in neuroscience and cardiology, quite honestly, is a curve that looks like this: strength duration curves. And this is the same thing. This is just another word for the same thing that you've just produced in your assignments. You do see a subtle difference here. It turns out if you stimulate with a positive going pulse and a negative going pulse, you get slightly different results, at least in nerve cells. I think this came from a neuron of some sort. So let's just take the red curve, and if you look at the area under the red curve, that's the region in which stimulus doesn't successfully initiate an action potential, right? So everything to the right or above, that stimulates an action potential. Everything to the left or below does not. So that's that gray region. And so we're trying to capture that description of the line in between those two regions, right? That's the whole purpose of this fitting. But it helps to then say, well, what is it that we're actually showing here, and how does that correspond to the physiology? And when you think about the area under a curve, right, that's the product. That's an integral of the quantities on the 2 different axes. And when we think about that from our physics perspective, if we think about integrating the current over some period of time, then that's the integral of current over time, and that's the definition of charge. That really is the definition of charge. I mean, you can see it the other way around. You can say current is the first time derivative of charge, and that's also a correct definition. It's the same interpretation of this equation, or different interpretation of this same equation. And so when we start to think about it, charge might be the quantity of some interest. It really, this integral captures that area. And then we can also recognize that the voltage that we care about, which is the threshold that initiates the opening of sodium channels, that threshold happens, that voltage buildup happens in a cell because we have charge and then we have some amount of capacitance. And of course, the value of capacitance will change how much voltage there is, a very simple relationship that we have. More charge means more voltage, and more capacitance means actually less voltage. So we can start to piece together kind of a logic behind all this. If we say, well, the area under the curve is charge, and charge is what I need to get to my threshold voltage, maybe there's some relationship there that I can play with. And so now if we say, well, integrals are fine, but I have discrete values, so I want sort of a discrete equivalent of an integral, and that, of course, is a sum. And for every element of that sum, every little piece of that summation of the area, we can say I have a charge, which is approximately equal to the current. So that would be the intensity of the stimulus at that point in the curve, times the duration, the delta t. Remember, because that x-axis is not absolute time, it's the duration of time used for the pulse. So those two quantities together are what give us an area, and they also give us charge. And so if we rewrite that equation and say, well, if we have current equals the charge over delta t, then we can also write it very explicitly as charge times 1 over delta t. And now, hopefully, you can see where this is headed. I even added in an I0 here. And why would I do that? Because I'm trying to reformulate the physical equation that describes the behavior of interest to something like a straight line. Y equals mx plus b. And if I look at those two equations together, they describe very nicely what it is that we can do with our data and then plot with our data and see how close we come to a straight line. Not only can we see how close we come to that straight line, we can even get the slope out of that straight line, and we see that that slope happens to be the charge. And if we're lucky, that charge is sort of a constant. And this makes sense too when you think about no matter how I get there, no matter how I achieve that membrane threshold voltage, it's always going to be a function of the amount of charge that's delivered to that cell. Capacitance stays constant. That's not going to be changing with time. So this really allows me to drill down into the key quantities that describe my underlying behavior, my underlying physiology. So now, if I take my original data and plot not delta t, but 1 over delta t, then I get a line that looks like what you see here. And that line, indeed, falls pretty nicely on a straight line, and the r² value gives us some confidence that it's a pretty good representation of a straight line. There is an offset of some sort, and that's kind of interesting to think about. But the point is that we have now also a slope, a constant slope. We can determine that slope from the data, and that slope turns out to be 30 nanocoulombs per centimeter squared. So the per centimeter squared, that's true of all the parameters that we use in these models. They're always normalized by surface area, just as capacitance is and all the other quantities. So this is a really useful quantity. This really tells us how much charge per surface area of that cell that I need to inject in order to successfully stimulate that cell. So here I've used the model to gain real insight into the underlying physiology. I've even been able to use the model to come up with a prediction for the amount of current and the amount of ultimately charge that I have to deliver. And it's given me an equation with which I can pick whatever combination of intensity of that stimulation and duration of that stimulation might be useful. And there might be engineering reasons. It might be that you could minimize battery drain if you picked a number that had, one combination of current and duration over another combination. This is how we use models to design devices and actually set parameters for those devices. So that's the kind of insight, that's kind of depth I want to encourage you to see about how you can apply that to all your simulations, whether it's the next homework or any simulation you encounter. Okay, problem 3. This was sort of an interesting one. This was a really reproduction, as I mentioned, of one of the original experiments done by Hodgkin and Huxley, in which they changed the exterior or the external sodium concentration. Easy thing to do in those squid giant axon preparations you've heard about, and so they could just measure or set the salinity, if you will. They could measure that, determine that, and then see how the behavior of the membrane might change under those conditions. And we can do the same thing very easily here with our model, and much more quickly. Now, all models, again, all simulation experiments you do should have a question or a hypothesis behind it. And one of the questions, and a hypothesis is sort of a question in disguise sometimes, but the hypothesis that we want to test is that the external sodium will have an influence on the action potential. That's sort of broadly true, and that's probably an easy one. But the more interesting one, and I asked you explicitly to do this, when we reduce that concentration gradient of sodium down to 0, when we make the external sodium equal the internal or the intracellular sodium, what happens? Because on the one hand, you could say, well, there's no concentration gradient. And if there's no concentration gradient, why should sodium move, even when sodium channels might open? And you'd be right in saying that there's a reduction in the drive. I'm trying to skate around the word here. In the chemical force, for example, in a situation would go to 0. But that's not really what we care about in electrophysiology. We care about the driving force, the driving force. And the driving force is not just the Nernst potential, because, right, if we reduce the concentration of external to match internal sodium concentration, the Nernst potential will go to 0. We have no chemical gradient anymore. However, we still have a difference between that 0 volts that the Nernst potential would be and the actual membrane voltage, which is still negative inside. So there is still a driving force because the Nernst potential is not the same as the membrane potential. And when that's a difference between those two, we call that the driving force. So a driving force still exists, even at very low concentrations of sodium. So that's one of the questions we need to ask. The second hypothesis, which a number of you formulated, was that, well, maybe there's another ion that would carry that positive charge into the cell and cause an action potential. And of course, the candidate is calcium. And indeed, some of you speculated that calcium was the case. Now, how do we use our model to answer those two questions or test those hypotheses? Turns out we can do it quite easily with this particular type of model. So here's a plot that shows you the situation when the external and the internal sodium concentrations are the same. And we see there's an action potential. It's not a great action potential. It's a little small, but it's long. It's not a terrible action potential. And if we look then at the currents below it, the sodium current in the middle, and then the mostly calcium current, the slow inward current at the bottom, we see that those both are non-zero, right? There is not a concentration difference, but there is a driving force, and so there is a sodium current that goes into the cell. Now, based on what you just learned before, you could ask the question, well, how much charge do I have there? I have a fairly large current from the sodium channels, but it's very short. So if I integrate those, I'll get an idea of how much charge comes into the cell. And that charge is what will give it the action potential shape, ultimately. Those same rules that applied when we're talking about the context of just barely stimulating a cell, those same physical rules apply to anywhere in the action potential. So if I have positive charge going into the cell, the membrane potential becomes more positive. And that's indeed what we see. That's the action potential going from its resting value up in this case close to around 0 millivolts. So that's a positive shift. We also see below it that the calcium current indeed flows and contributes, of course, to bringing positive charge into the cell. And in this case, we don't have just a spike of high intensity. We have a lower intensity, but over a longer period of time. So we could do the same calculation. We could figure out what the area is under both those curves, and that would tell us how much charge each contributed to that action potential. And that would give us further insight into what the balance is between those two sources of positive charge coming into the cells. And the potassium currents to the right, they're doing their normal thing. This is what they do. They turn on, IK you see gets bigger and bigger in order to repolarize the cell, or has the effect at least of repolarizing the cell. So those all look, somewhat different, but have their sort of normal shape that we've been able to see in other simulations. Now again, we have these sort of questions, and we can drill down even more. So we can zoom in on that early part of the action potential, ignore the potassium currents for the moment, and focus just on the action potential voltage and the two responsible currents. And there we see here that indeed the sodium current is present. It's short, but it's pretty big. So this is where scale comes in. If you look at the scale on the two axes that contain currents, one of them is an order of magnitude larger than the other. And so we have to be very careful how we view these data and make sure we weight them appropriately, because scale matters, of course. It matters in our plots, and it can be especially misleading if we don't look very carefully at the scale that our plots give us. And of course, MATLAB scales automatically. And great, that makes life easy for us, but we still need to be able to interpret that, to look carefully at the scale. Because you see in this rather terrifying image, scale matters. This little critter, I believe, is like a mite or something very harmless to us, tiny, 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 microscopic. We can't see these without a microscope. But blown up like this, they're terrifying. Here's another rather odd-looking creature. That strand through the middle is a human hair. So scale matters. That's, matters in how we perceive things and hence how we should interpret them. So, what should we do better next time? I think there's a systematic approach that I want to encourage you to explore. Here's a figure that I found just doing a literature search on how to plan a simulation experiment. It's specific to a certain application. Our application's a little different. But this goes back to, the original figure goes back to 2008. Or actually, no, 2006. So this is an old figure. I mean, we've been thinking about this for a long time. So there are strategies out there that you can read about, learn about, and try to make sure your simulations work effectively. So how do we use this for our simulations in our context of this course? Well, in some regards, the nice part is that we have a part we have to do. So our part means what I have to do and the TAs have to do to prepare this question for you. And we're going to have specific goals and objectives we're going to ask you to try and use the simulation model to achieve. So I'm going to give you some questions to answer. That should make it a little more straightforward than if you're doing this simulation yourself. We're going to give you the model, so you don't even have to choose the right model. Otherwise, in any kind of practical situation, you would have to decide what's the right model and how do I turn all this math into the right numerical version that I can run in a reasonable amount of time that has the characteristics that are most important for me for the questions that I'm setting out to answer. So these two parts are a key part of the planning process that we'll look after. Now, your part is to then look at these models and say, okay, what are the variables that I have at my disposal? How do they relate to the questions I'm supposed to address? Obviously, I'll have independent variables. These are ones I can control. Those will generate results in terms of dependent variables. And we have to be careful that those are meaningful, that we pick those carefully. And then once we get this high-level idea, then we have to design the experiment. I love this notion that designing experiments is not just something you do in a wet lab or something you do in an exercise lab like we're going to do. This is something that also plays out in terms of simulations. So you have to plan your experiment. You have to design how you're going to set parameters, which ones you're going to hold steady, which range are you going to use, what steps between those parameters, if you're going to scan through a range of parameters. Those are all decisions you have to make based on the questions you're trying to answer, based on the model you have, based on how much time you want to invest. All these things can play a role. And it's complicated. There is no simple answer here, but there has to be that strategic part of the process to get anywhere. Finally, once you have results, you have to analyze them, of course. So as I just explained to you in this previous example, there's a lot of analysis often that we don't initially think of. And analysis oftentimes takes, again, sort of back and forth between what I'm seeing with what the theory is behind it. How do I correlate those? How do I probe those data? How do I maybe manipulate the data to get what I would call secondary results? So you don't just plot directly what comes out of the model. You might derive something from those quantities that the model generates and plot those and look at their relationships. And they may tell you something useful. Just like this simple case where I took the threshold, the stimulus duration, and I flipped it. And I went over the stimulus duration and got this nice linear function, and everything made sense and correlated nicely with my theory. So this is the kind of analysis that is very situation specific and can be quite challenging for sure, but is where the intellectual sort of profit lies. So if you can get into this way of thinking about things and develop your skills in this is super, super valuable for your own research, your own graduate degrees, and your careers that follow. So we're going to try to encourage that throughout the semester. So you can take some very concrete steps as well. So these are sort of high-level strategy things. Now I want to get into kind of tactics almost here. One of them is, how do you organize the results you get in a sensible way? So again, this goes back to what I talked about at the beginning. We have certain structures and guidelines in technical writing that we have to respect if we want other people to understand what the heck it is we're saying, right? And so we have to make sure we follow those guidelines, and then we have to make sure we actually have a question and then we answer the question. So if the homework assignment says, answer this question, then obviously find a way to answer it. And if it answer isn't obvious, then ask us and we'll help you. We'll guide you into that. But there'll always be questions to answer. Continue to use the tools that you have, Grammarly, other AI tools. I've been experimenting with them. None of them write great text right out of the box, but they can be useful. And Grammarly definitely draws my attention to passages that things are a little rough, where the grammar is not quite clear, or obviously where the spelling is not correct. So continue to use those tools and continue to find a clear and concise way to capture your thoughts. And again, there are lots of materials I can point you at if you have more questions about that. We have a whole course for PhD students on proposals that get into some of these writing mechanics, if you will. So they're really important, and this is a lifetime learning skill. I definitely still think I have improvement I could make in my writing, and I seek to find new ways to write better all the time. But our goal in this course is just to see progress, to see you getting better with your writing. That's what's really important to us. Clear graphs, clean, using color, good captions, all those things that I talked about before. Make sure that you spend some time on the figures. They will take time. As they come out of MATLAB, they're rarely actually very good. There's almost always some adjustments you have to make. So learn how to make those adjustments. MATLAB allows a lot of that, supports a lot of that. And so I encourage you to get good at those particular tools. You'll use them again and again. This is not something that's just for this course. And with that, I think we've covered the main parts of what I want you to think about as we move forward. We're going to have another assignment, a whole heart modeling assignment using a different piece of software, and I hope you take some stock of how you did. Look at your own report the first time. Look at our comments, and then figure out, okay, how can I make everything a little bit better? That should always be our goal. Keep improving, keep learning, and keep working together and sharing our ideas so that we learn as a group and that you each learn individually. Okay, with that, we'll wrap this up. Thanks so much for your attention. Look forward to seeing you again soon. Bye for now.